There he goes. All right. Okay, well, we are looking at, maybe I'll angle my, no, it's still all there. That is, anyway. All right, numeric optimization. That's today. It's Friday of week 7. We only have like just a few weeks left then, huh? So next week, we don't even have a Monday, so you get 2 lectures then, and then you get 9th week and 10th week, so that's what, 8 lectures remaining. And then you got finals, and then spring break, and then spring quarter, and then 1 more year. Okay, well, anyway. And then work for the rest of your life. Well, no, just, okay. It's anyway, it goes by quickly. Today's actually my father's birthday, but he's in Japan, and I forgot to call him yesterday, so it's going to show up at, the day after. Yeah, the bad son. Okay. Anyway, today we're bringing up golden section search. We're still talking numeric optimization. So golden section search is based off of the golden ratio, all right? And so, I don't know, I think you know about the golden ratio and how it just shows up all over the place, right? And they always show you like a picture of what the nautilus shell and sunflower seeds and the Fibonacci thing, and then they always say math is beautiful and it shows up in nature, and I guess we're supposed to say yeah, but the idea here, as far as the golden ratio goes, is that here, if you take some rectangle, okay, and one side has a length of 1. Okay, so this part's a square. So this side has a length of 1, and this side has a length of 1. Okay, and then, I'm sorry, the long side has a length of 1 plus x, and the short side has a length of 1. And the idea here is if you cut off this square, the rectangle here has the same proportions as the original rectangle. Okay? So that means to say that when you look at this rectangle over here, and you look at this square, which will have sides of x, okay, and this length over here now has a length of 1 minus x, we're going to say the ratio between any of these segments, blue to yellow or blue to red or yellow to red, they're all going to remain consistent. So you do 1 to 1 over 1 plus x is going to be the same ratio as x to 1, or 1 to x is the same as x to 1 minus x, or whatever it is. Okay, so we're going to say blue over red is going to be the same as blue over red. So if I do 1 divided by 1 plus x, that's going to have the same ratio as x divided by 1, and that's kind of the definition of the golden ratio. So what is this value x? Okay. So if I do this, 1 divided by 1 plus x is equal to x over here. And then if I solve for x, so multiplying both sides, I get 1 is equal to x times 1 plus x. And if I multiply this out, I get x squared plus x minus 1 is equal to 0. And using the quadratic equation to solve for this, we're going to get x is equal to negative 1 plus or minus the square root of 1 squared plus 4 over 2. And we have negative 1 plus or minus the square root of 5 over 2. If you look at the picture, x is a positive value, so that means we're going to take the plus, all right? And so in this case, we get x is equal to 0, something around 0.618. And that is to say that if we do 1 to 0.618, that's going to have the same ratio as 1.618 to 1. So if we do 1 divided by 1.618, that gives us 0.618. And also interestingly enough, or not interestingly enough, this is part of the definition, if you take the other side over here, and if this is 1 and this is 0.618 and this is 1 minus 0.618, okay, 1 minus 0.618 is 0.382, and that's also going to be 0.618 squared. So just kind of how all of these ratios work out. Okay, so why did we talk about the golden ratio to begin with? Well, it's useful because we created this optimization algorithm that takes advantage of kind of these properties of the golden ratio, so that we don't have to repeat our calculations all of the time. Okay, so we're gonna do this golden section search, and let's say we wanted to find the minimum of this function here. Okay, so this is x squared minus 0.8x, and I'll just tell you the minimum's at 0.4. Okay, but what we're going to do is we're going to start off with some interval, and we're going to assume that a minimum exists, at least a local minimum exists somewhere inside this interval. Okay, and so we're going to just say, let's go from 0 to 1, and we're going to see if we could find a way to narrow our search for a local minimum here. Okay, so we're going to select an arbitrary interval with the assumption that the minimum value, a local minimum, exists somewhere between the endpoints. You know, let me make this bigger here. Okay, so we're going so 0 to 1, and what we're going to do is we are going to look at two inner points. Okay, so we've got whatever endpoints we have, where I'm going to call that my lower side, my lower bound, and my upper bound, and we're going to search for two inner points, which I will arbitrarily call x1 and x2, and how we label these things is arbitrary. I'm going to do the lower plus this thing to be x1 and the upper minus this to be x2. You know, I could have just as well kept calling it x1 over here and x2 over here. But the idea here is this point x1 is, so if we say the golden ratio is around 0.618, this is going to be 0.618 of the way across from the lower bound to the upper bound. And then this point x2 is going to be 0.618 from the upper bound down to the lower bound. So here I'm going to just take the golden ratio, something around 0.618, multiplied by the difference between the upper minus the lower, and we're going to add that to the lower bound. Okay, and then over here, x2 is I'm going to take that ratio 0.618, multiply it by that difference, upper minus lower, and then subtract it from the upper bound. Okay, and so we're going to get this. So we take the distance from upper to the lower, and we go 0.618 up to here, and then 0.618 down to this side. And so this is what the values get evaluated to. Okay, so we find x1 and we find x2, right? And here in this picture, you know, we can see it very clearly, you know, that where the minimum and stuff should be. But keep in mind that when we're doing this search for the local minimum, we generally don't have a graph for us. Okay, we just have this, we're just under the assumption that a local minimum does exist between the lower and the upper bounds, and we've just evaluated the function at two inner points, x1 and x2. And what we find is we find that x2 is less than x1. x2 is less than x1. So what does this mean? This means we can eliminate everything to the right of x1. Everything to the right of x1. Because the idea here is that we're under the assumption that a minimum value exists somewhere between the lower bound 0 and the upper bound 1, okay, or just the lower bound and the upper bound. And again, we're going to just we're under the assumption that there's just one of these things. And so if we compare x1 and x2, and x2 is lower than x1, we can say, well, the lower point has to be somewhere between the lower bound and x1. And it's not going to be to the right of x1 because we know that there already is a point that's less than x1 on the left of x1. Okay, we know that there's already a point that's less than x1 to the left of x1, so we're not going to bother searching to the right of x1. Okay, so we're going to throw away about, I guess, 38% of my search interval, okay? And we're going to throw this side away. And we're going to say, okay, we're going to search for the minimum somewhere between this left bound, the lower bound, and now my upper bound is going to be x1. Is that okay? So we eliminate the area to the right of x1, all right, and we set the boundaries of our interval to be from the lower bound to x1, okay? Okay, so with this, what do? So we're going to, so if this is my lower bound now, and this is my upper bound, x1, okay, I want to find two inner points, okay, the lower bound to the upper bound. And this is where kind of the beauty of the golden ratio comes in, okay? Because if we think about this location of x2, this location x2 was originally about 0.618 of the way from 1 to 0, okay? So this is about at 0.382. Now that I've said x1, which is at 0.618, is my new upper bound, and I ask, okay, where would my inner points be? My inner points, I want a point that's 0.618 of the way from the lower bound to the upper bound, and I want a point that's 0.618 of the way from the upper bound to the lower bound. Okay, so this, what used to be kind of x2 over here, this is going to become my new x1, because this is located at 0.382. 0.382 is the same as 0.618 squared. Okay, so this is now 0.618 of the way up to 0.618, okay, which is now my new upper bound. So my new upper bound is 0.618, and this point is now 0.618 of the way to 0.618, right? And so because of this, so the reason why we want to do this is so we don't have to repeat calculations, right? Because one thing is I could have just said, hey, let's just pick 2 points in the middle and kind of do this left and the right-hand comparison. But then I'd have to, every single time I do another iteration, I have to recalculate 2 points in the middle, okay? Now, for a function like this, it's not that big of a deal. But what if your function is this really complicated thing? What if it's like the sum of like this series, you know, an infinite series, and you say, well, we're not even going to bother with the infinite series. Maybe we'll calculate the first 1,000 terms, okay? Even that might take a long time to do. And so if you say, well, I have to, okay, now I have two inner points and I have to calculate the value of these 1,000 terms for this point and the value of the 1,000 points for this point, that's a lot of computation. But if we can take the value that I've already calculated before, because in the previous iteration, I calculated what x2 is and I calculated the value of the function at x2, if I can just reuse that, and now I only have to calculate one new value, I've effectively halved my work, okay? So I can reuse this value. The old x2 is my new x1. I don't have to recalculate its location. I don't have to recalculate the value of the function at that location. Okay, so this is going to save us some computational power. And so now I only have one new point to evaluate, okay, and that will be the new x2. Okay, so I have my lower bound at 0. My upper bound is at 0.618. My new x1 is at 0.618 squared, 0.382. And then I have to calculate a new x2. So this is going to be, 0.618 of the way from here down to 0. And that ends up being 0.236. So this is a new value. I have to calculate the value of the function here. And then when we calculate the value of the function here, we find that this is greater than the value at x1. So what we do is we are going to eliminate everything to the left of x2. Okay, so we're going to throw all of that away. And now this point, which is here, is 0.618 of the way from here down to here. okay? Because of this golden ratio thing, I can still reuse this. So this, what used to be x2 is going to become my new lower bound. My upper bound remains the same, and what used to be this inner point here becomes the new inner point, but on the lower side. I have to calculate a new x1 over here, which is going to be 0.618 of the way from 0.236 to 0.618. Okay, so we eliminate that side, and so now this is my search interval. I calculate the value here, okay, and I evaluate these two things, and I say which one is greater, and we're going to find the blue side, x1, is a little bit higher than the value at x2, so now we're going to eliminate everything to the right of x1. So we eliminate everything to the right of x1, and then this point over here becomes my my value, okay? And then I have to calculate this one on the left, and then we can, when we evaluate this side comes out higher than this side, so we throw away this side. This value here, this inner value, gets reused, so I don't have to recalculate anything. We can see that line stays at the same location. I have to calculate this new location. We compare these two things, and it's hard for us to tell in this picture, but we say, oh, you know what? This side is a tiny bit higher, so we're going to throw away the left-hand side over here. And again, we can see this line right here gets reused, and we calculate a new value over here. When we do this, we're going to find this side gets thrown away, and then you can kind of keep going, and you can see the interval gets smaller and smaller, and it stays focused. It's honing in on this value 0.4, which is at our minimum. Right? So we're reducing our search area by around 38% every single time. Okay, so we have linear convergence here on the thing, and there's kind of a lot of similarities between this and bisection method. Bisection method is a root finding method. Golden section search is an optimization thing. It's going to find a local minimum, but it has kind of this. It doesn't depend on any kind of derivatives. It doesn't, and it's as long as there is a single minimum inside the interval when you start off with, it will converge to it. Okay. So the golden section search is very robust. If a minimum lies within the interval, it will find the minimum. If the minimum happens to lie on the interval boundary, it will converge to that boundary point. If you have multiple local minimum in the interval, then the algorithm will just end up kind of finding at least one of those things. We'll converge to one of those things. Okay. Multiple termination conditions are possible. Like, how do we get this thing to stop? Okay. And a common choice is you just say, well, let's take the difference between the upper bound and the lower bound, and if the difference between the upper and lower bound is within some tolerance level, right? If the difference between upper and lower is, say, less than 10 to the negative 7, we'll call it a day and say this is where we found the minimum. Okay, and that's that. Do we have any questions about this? I've already included in the R code to run golden section search. Okay, so the R code to run golden section search is has been uploaded to Canvas. Let me give you I haven't given you any view quiz answers, right? Okay, first view quiz answer today is D. D as in dog. D as in dog is your first view quiz answer. D as in dog. All right, so that's golden section search. Here's the code for it, and so here I think it's pretty straightforward, and I've just added a whole bunch of comments to make it easier to read. Okay, and this code was written by another person, Eric Kakai, and I kind of modified it to line up with the notes that we have. But basically, you just start off with some arbitrary function f. You have a lower bound and upper bound, arbitrary tolerance level at which point we're going to quit. The golden ratio is phi. Okay, -1 plus square root of 5 divided by 2. This is going to be 0.618. And x2 is the lower bound plus phi times the difference between upper minus lower. x1. x2 is upper minus phi times the upper minus lower. And so the arrangement of points is lower, x2, x1, upper. We're going to evaluate the function at x1 and x2, and this will be f1 and f2. And if f2 is greater than f1, that is, if x2 is greater than x1, we will throw away everything to the left. Then x2 becomes the new lower bound, x1 becomes the new x2, f1 becomes the new f2, so I don't have to recalculate anything. The only thing I need to calculate now is the new x1 and calculate the function at x1. And on the other hand, if it's not, then we'll throw away the other side. I don't have to recalculate f1, but I do have to calculate a new x2, calculate the function at f2, and we do that. And then we just repeat over and over and over again, okay? And we're going to keep going until this difference between the upper and the lower bound is less than some tolerance. And then we'll quit, okay? And we'll print out converged and blank iterations. And then the estimated value that we will report will just be the midpoint of the lower and upper bounds. Okay, so if we take that function x squared minus 0.8, it tells me the value it converged to is 0.399999. If I lower my tolerance level, then it takes a few more iterations. So if I want my tolerance to increase by a factor of 10, so from 10 to the negative 5 to 10 to the negative 6, it takes about 5 more iterations, okay? 10 to the negative 7, 10 to the negative 8. So 10 to the negative 5 I get in 24 iterations, 10 to the negative 7 I get in 34 iterations. It takes another 10 iterations. And part of the reason for this is if you every time we do it, our interval is around 62% of the previous interval, okay? So if you do 62% phi raised to the 5th power, that's around 9%. So every 5 additional iterations, your resulting interval will be about 9%, a little less than 1/10 of the previous interval, okay? I guess the interval 5 iterations earlier. Okay, let's take a look at another method. This method is called coordinate descent, and this is very exciting for me. I think, I don't know, every time I introduce some of these new algorithms and things, I get very excited because I think they're so cool. I don't know how you guys feel, but so far all of the optimization stuff, we talked about finding an optimum using a derivative and finding optimums using golden section search, and these have all been done on univariate functions. Okay, they've all been done on univariate functions, and technically optimizing on a univariate function is probably really, really, really easy, okay? Even if you didn't know anything about optimizing, okay, you could just graph the function, right? You could just say, hey, let's go from 0 to 1. Let's evaluate the function every 0.01, right? So I'm just going to evaluate it at 101 locations from 0 to 1, 0, 0.01, 0.02, 0.03. You can just take all of those values, and then you just say, oh, that's the lowest one. And that'll get you pretty close to the answer, okay? So, you don't actually have to do all of this work in a lot of cases, right? So, one thing is you've got some function, and you could just do, say, from -3 to 3. Even if you do it at intervals of 0.001, that's what, 6,000 values to evaluate? You can say, hey, which value is the smallest, right? You evaluate the function at 6,000 locations. Which location is the smallest? And it says, oh, the smallest happened at 0.4, okay? So that's simple. What if you wanted to do this for a multivariate function, though? Okay, for a multivariate function, you could do the same kind of thing. We call this a grid search, and you could say, all right, let's evaluate 6,000 locations from -3 to 3 for x, and let's also look at 6,000 locations from -3 to 3 for y. Okay. Now, if you do that, how many locations total do you have to search? Now you have to search 36 million locations, right? 6,000 times 6,000 gives you 36 million. Now you have 36 million, like all these little points to search, and that's a lot, right? What if you have a three-dimensional function? Okay, now you have to do 36 million times 6, and what's that? That's 216 billion. Okay, this grows exponentially every single time you add a dimension. So grid search, great for a univariate function, but pretty bad for anything of higher dimensions. And so what we can do for higher dimensions is we can use this thing called coordinate descent, okay? And basically what coordinate descent does is we will take the function and optimize it one variable at a time. So we're going to say, let's lock the function in at, say, x equal to 3. At x equal to 3, your function of xy, if you lock in x equal to 3, it basically reduces it to a univariate function of y, right? You turn x into a constant. Now you have a univariate function of just one variable, y. And then you say, let's find the value that minimizes this univariate function. And it's going to say maybe y is 2. And you say, okay, now y is 2. We're going to lock in y is 2. And then let's optimize the function. So y is now a constant of 2. Now this is a univariate function of x. Let's optimize the function in x. And we just repeat this process, doing locking in the other variables so that it becomes we turn the multivariate function into just a univariate function of one variable at a time. And we kind of go through each variable or each coordinate one at a time, optimizing each one, and you end up kind of getting this little bit of a stair-step pattern. And so to illustrate this, I have some code here. Let me see if I can make this a little bit bigger. So I'm going to load up my golden search function, okay? And so golden is basically that golden section search where we plug in a function, a lower bound and an upper bound, and then what it's going to return is the value that minimizes the function. All right, this is going to be the function that I wish to optimize. It's a two-dimensional function. It's a function of x and y. And it's going to find x squared minus 2x minus 0.5xy plus 2.5 y squared. Let me just show you what this looks like. Let's go to Wolfram Alpha. Huh? Okay, there we go. All right. Okay, so it's this doesn't look quite right. I don't know why it looks like this, but it's an elliptic paraboloid, which let me show you what an elliptic paraboloid is. Okay, it's one of these things. All right, so it looks like a little bowl, okay, of like an ellipse, right? So it's like your salad bowl or something, but shaped like an ellipse. So it's not practical, but it looks kind of like that, and there we go. Okay, so anyway, I will what I'm going to do. I'm going to create this plot using this package called Plotly. And let's see if we can get this going here. All right, so this is kind of This is what it looks like, and you can kind of see, it's a little hard to see, but we got these concentric ellipses. Is that even the right term? Concentric ellipses? Or so you have these kind of this is what it looks like, and you can see kind of, I don't know. All right, you guys can visualize this, right? So this is and this is cool, right? This is Plotly. Don't use Plotly for your homework. It's like cool for demonstrations, but like not for printing. Okay. All right. So I'm going to just arbitrarily start at this location. X is -1 and y is 1.5. And what is it warning me? It's warning me about something here. Okay. So this is the location. This little yellow dot right here is x is at -1 and y, here, let's see. So x is at -1 and y is at 1.5. Okay? And what we want to do is we want to get down to somewhere, the minimum is somewhere around here. So we're going to start here. And what we're going to do is we are going to we're going to choose one of these things, and let's say we'll hold y constant at 1.5. Okay, we're going to hold y constant at 1.5, and we're going to find the value of x that minimizes this. So if I plug in, this is the function x squared minus 2x minus 0.5xy plus 2.5y squared. I've done a bad job of this, okay? And intentionally bad, because part of your homework is to write some code for coordinate descent. and so I didn't want to give away the answer here in this demonstration code, but I wanted to show you how it looks. So basically, I've taken our function. I'm going to say y is equal to 1.5 and return, now it's a function of x, return whatever this is, where now we're plugging in 1.5 everywhere for y. Okay, and so if I do this, I can add this trace to the line, or to our plot here. Okay, and so here it is with y locked in at 1.5. That's this blue line right here. Okay, so here x is at -1, y is at 1.5. We're locking in y at 1.5, and we want to find, okay, what is the minimum of this blue line? Now that I've created a univariate function in blue here. Okay, so I'm going to use golden section search. I'm going to use golden, and I'm going to use this function, the function I've called g iteration 1, and we're going to search from x equal to -1.5 to x equal to 2, and we ask, what is the value of x that will minimize this thing? Okay, and it comes back and it says the value of x that will minimize this blue function is at 1.375. So somewhere right around here, okay, 1.375. So I'm going to go ahead and add a dot to show you the point here that minimizes this function. All right. So we've turned this into a univariate function. The value that minimizes this univariate function is right here, this yellow dot. Okay, so if you look at this is the lowest that the blue function, the blue line gets. Okay, so now that we have that, what do I do? We're going to lock this value in at 1.375 and draw a trace there. Okay. So here is, so locking in this value 1.375, this is the trace of the function. And we're going to ask, what is the value of the function that minimizes this univariate parabola? This, if I were to just look only at the purple line here, okay, what function minimizes that? Okay, so we're going to just trace this until it's as low as possible. So using golden section search, I'm going to do my function I'm calling g iteration 1b. X is locked in at 1.375. It returns the value of our parabola there. We're going to search from y is negative 1.5 to 2. And it says when x is 1.375, the value of y that minimizes this is going to be 0.1375. 0.1375. Okay. All right. And so we will plot that. Okay. Does this kind of make sense? What we're doing here? We're locking in one variable at a time. We're turning these into univariate functions, and when you have a univariate function, we're going to find the value of y or x, the other variable, that minimizes it, right? So if we were to look at this here, we can see this marker happens at the location where purple is at its very lowest. Okay, it's not necessarily where the entire ellipsoid is at its lowest. The ellipsoid's at its lowest over here, but we're getting kind of closer and closer to it. Okay, minimizing one thing at a time. Okay, so we're going to repeat this entire process. Now I go back and I'm going to say, okay, we're going to lock in y equal to 0.1375. And then let's add the trace there. And let's plot all of that. Okay, and so here I think I've done 2 steps at once. I've locked in y equal to 0.1375, and I got the green trace, this green trace right here, okay? And we're asking, where is this function minimized? Okay, this function is minimized. If you look at this green line, it's minimized just a little bit to the left, where x is equal to, what is x? X at this point is 1.034, okay? So this is, we're right here, okay? And we would repeat this over and over and over again, and eventually we will converge to kind of the global minimum on the actual paraboloid itself, okay? So we started off here, we traced it, and we locked in the y value with this blue line, and we said the value that minimizes the blue line is right here. And once we found that, we locked that x coordinate in, and we minimized along this, in kind of the next direction, we said, what is the value that's going to minimize this? And we got down to here. Now that we found here, we locked this value in, and we minimized along the green line. And then the next thing we would do is we would lock in this point, and we would trace along some traced here to minimize it, and it will probably end up just being ever so slightly different at the next point, and we would iterate repeatedly. And I think at this point, the markers that I'm using to mark the locations are a little bit too big, where they're all just going to overlap on top of each other. But hopefully that gives you the idea of how coordinate descent works. Okay, so it works really great for ellipsoids. It works great for what we call convex functions. There's a whole bunch of functions that you could try to use it on intentionally to try to trip it up, right? So if your function has kind of this weird surface to it, going just one direction at a time could end up getting it stuck. But it works pretty well for a lot of cases. And so you have an exercise in your homework where you're going to write a function to implement coordinate descent, and you're going to end up tracing out this kind of stair-step pattern through your graph surface there. Okay. How many view quiz answers have I given you? Just one. Okay. I didn't do a good job today. Let me give you your last 2 then. Last 2 answers will be E as in elephant and A as in apple. E as an elephant is your second one. A as an apple is your third answer. E as an elephant, A as an apple. Okay, and that will be it. Plotly is a cool piece of software to draw stuff. It's pretty cool, but yeah, don't use it in your homework. All right, you can play around with it. Yes, question.
What's the termination conditions for it?
Yeah, the termination condition generally is when at the next iteration, if I guess you look at, you can, I mean, there's a whole bunch of things you can look at, right? You can look at the change in x, the change in y, and if both of those are less than some tolerance level, then you can stop. So if your change in x and your change in y are both less than, say, 10 to the negative 5 or whatever, you can say, all right, we've reached a point where we can stop. Or you can say the value of the function at your current location and the value of your function at your previous iteration, if the change in the value of the function itself is also less than a certain thing, you can stop there. So lots of things you can use as a termination condition. Okay, we'll go ahead and end here. Have a good weekend. We'll see you on Wednesday. All right, enjoy your extra day off.